So, welcome back student to the next class of complex analysis. In the last class we started something called Laurent series. So, let me once again remind you, if z is a function, I can expand this function in this particular power series where k running from minus infinity to infinity, and it is restricted over some annular region, and the coefficient of ak was something like 1 by 2 pi I closed integral f xi minus z0 d xi with k plus 1 here, and then we expanded. So, that was the statement, and then we try to expand few function for a given in some given region. So, we will go with that. So, we need to solve few other examples also. So, let me go with that for more example. So, fz, this is example, another example of Laurent series. So, it is something like z multiplied by z minus 3, and the region that is given is something like this. Z minus 4 with this. So, this is a restricted boundary, and we need to expand our function with this condition. Now, if I want to do that, we will do the way we have already done these things so far. So, we will just separate it as say 1 by z minus 3 minus 1 by z. If I do, then this z comes here, z minus 3 comes here, z will cancel out, but one extra 3 term we will have here. So, these 3 I need to take care with this 1 by 3 term. So, this 1 by 3 is this. Now, I need to make my problem in such a way that I can have this z minus 4 term and this. So, here if you remember that 1 divided by the restriction suggests me that 1 divided by z minus 4, this is less than 1, that is one condition, and another condition is this quantity divided by 4 is less than 1 as well. So, I need to use these two condition and then expand this. So, that is the trick to solve this kind of problems. So, z minus 3 I can write z minus 4 plus 1, I can write this. Another part I can write, which is z, I can write z minus 4 plus 4 like this. Now, I can expand this term because here I can have 1 divided by z minus 4 less than 1. So, if I take 1 by z common, anyway 1 by 3 term is already there. So, separately if I do this quantity, so let me write it right hand side. So, I am expanding only this term. Z minus 4 plus 1, taking this I am expanding. So, if I take z minus 4 common, then it will be 1 plus 1 divided by z minus 4, this quantity. Now, I can expand that. Now, I can expand that. In the similar way, in the right hand side, if I take 4 common minus 1 divided by, say, if I take 4 common, then it will be 1 plus z minus 4 divided by 4. So, once I have 1 divided by z minus 4, because I required these things, and in other case I have z minus 4 divided by 4 because I required this, I want to use this condition from the given 2 condition, and the 3 term as usual is there. Now, we are done. So, now we need to just expand this. So, it will be 1 z minus 4, let us put 3 here, and then it will go to up. So, 1 plus 1 z minus 4 whole to the power minus 1, this is the first term, and the second term will be minus of 1 by 12 1 plus z minus 4 divided by 4 whole to the power minus 1. Let us check once again everything is correct or not. So, z minus z into z minus 3, I divided into 1 by z minus 3, z goes here, z minus 3 goes here. So, z will cancel out, we will have only 3 term, and I divided this by 3, so that these 3 term cancel out. Then I write this at z minus 3, I write z minus 4 plus 1, so that I can have z minus 4 term in my hand, and here only z is there. In order to have z minus 4, I take z minus 4 plus 4, so that the final term is z. Now, I take z minus 4 common out of here, then 1 plus 1 by z minus 4 here, and I take it as to the power minus 1, and here also it goes to upstairs, and I have this. So, now if I expand, let me erase this. Now, if I expand, it will be something like 1 divided by 3 z minus 4, then this series which is 1 minus 1 by z minus 4 plus 1 by z minus 4 whole square, and so on. This is one series, and another series that will have for the other term. So, let me erase this part. It will be minus 1 by 12, and then 1 minus z minus 4 divided by 4 plus z minus 4 square, 4 square, and so on. So, this is my entire series. This is the Laurent series, and if I use this Laurent series, then the terms will be something like this. So, here the residue is coming like z, the residue, that is the coefficient of 1 by z minus 0 is comes out to 1 by 3. So, we will come to this point later. So, let us first try to understand how a function can be expanded in terms of Laurent series. So, we are doing few problems last class also. Today also I am planning to do few problems, so that you are familiar with this procedure and know how to expand. So, next is another problem I have in my hand, which is fz is something like 2z minus 1 divided by z cube minus z square. So, we have this quantity or this function in my hand, and the restriction of this function is mod of z is greater than 0, less than 1. So, it is better that every time you have you check where we need to basically expand this function. So, if I have a circle of radius 1, so this is the circle of radius 1. So, the region I should cut this 0 point and also 1 point. So, the region annular region is here in between these two rings, whatever the region where we need to expand this. So, process is similar. So, 2z I can write it as z plus z minus 1 divided by this quantity I can write z square multiplied by z minus 1, and again divide the two term as z divided by z square z minus 1 plus 1 by z square. I have this quantity plus this. So, now if I write 1 divided by z minus 1 plus 1 by z, I have two term, but this term again I can simplify, and if I simplify it will look like 1 divided by z minus 1 minus 1 by z, this z goes here, this z minus goes here, with a negative sign z will cancel out, we will have 1. So, I can factorize this quantity in this way, plus 1 by z square as usual, it was 1 by z square because I am writing 1 by z square. So, I have three term, 1 divided by z minus 1, 1 by z, 1 by z square, but my limit, my restriction of z is that z should be less than 1, then it is done. So, once I have this, then there is no such problem, because I can expand these things like this way. So, it will be just say first term is 1 by z, I take this because I have nothing to do with these things, 1 by z is already there, plus 1 by z square, it is already there. Another term is I write minus 1 minus z to the power minus 1. I take minus common, then it will be 1 minus z, and I write 1 minus z as 1 minus z to the power minus 1 with a negative sign here. Then the expression is something like 1 by z square minus 1 by z minus this series. This series I know is true for mod of z less than 1. So, the restriction is already given to me. So, I am allowed to expand this series. If I do, then it will be something like 1 by z square, z plus z square plus z cube and so on. Now, the total series is something like this: 1 divided by z square minus 1 z minus 1 minus z minus z square and so on. So, you can readily understand that this part is your principal part, and the rest part starting from minus 1 is your analytic part, AP. So, I can just divide this principal part and analytic part. Again, this 1 by this term is important. I will come through this point again, because this is the residue of these things. Okay. Let us stick with this function. Now, I am going to change the region and then try to find out what is happening. So, now next the same function, but now the region is been changed. It is z minus 1 mod of z minus 1 greater than 0 less than 1. This is the problem that is in our hand. So, that means if I try to find out the region, z equal to 1 point is here. If I make a circle of radius 1, it will be something like this. It will not going to cut the 0 point, and another small circle here because it is greater than 0. So, z minus 1 greater than 0, that means I will have a small circle here. So, this is the annular region where I try to expand this function. This is the annular region where I try to expand this function. Again we will do the same thing by expanding this particular function, into some functions which are in this form. So z plus z minus 1, because z minus 1, z square, z minus 1, exactly the same way I am doing. I am repeating the problem that I have already done. So same old calculation, and I reached this point. Okay, so this is the same thing that we have done for the previous case. Again I am doing the same thing, just doing this way. So now the question is, the problem is I need to use these things, z minus 1 mod of z minus 1 is less than 1. I need to use this condition. Here we have z minus 1 here, so I do not need to do anything with these things because already it is less than 1. What about this z? I need to somehow introduce a plus 1 and minus 1 so that I can have this term, and then 1 by z square. That is interesting, So we will do that later. So let us first deal with this thing. Let me erase the function because this function is now written here. So if I want to expand this 1 by z with this limit, how to do that? I will take this function as this 1 plus 1 minus 1 plus 1, z minus 1 plus 1, it is something like this. So then how to deal with that? So 1 divided by 1 plus z minus 1, and once I write this, then I am done. If I do that, then I can write it as 1 plus z minus 1 whole to the power minus 1. I can now expand because my mod of z minus 1 is less than 1. So I can expand this series and it will simply comes out to be 1 minus z minus 1 plus z minus 1 square minus z minus 1 to the power 3 and so on. This is the functional form we have, and so let me erase these things here. I should write the function somewhere. So this is the form. I will write the function again, once again. So this form is nothing but, if I write in summation form, it will be z minus 1 whole to the power k minus 1 whole to the power of k, k goes to 0 to infinity. So this is the form, the summation form I have. 1 by z I calculate, and I find now the sign is repeating. So since sign is repeating, when k equal to 0, I have this is 0, this is 1, when k equal to 1, this is minus 1, when k equal to 2, this is 1, and so on. So now once I have z, then the question is, so let me write it here, what value I am getting here in the summation form. In the summation form, I am getting z minus 1 whole to the power of k minus 1 whole to the power of k, k goes to 0 to infinity. Next thing I will do, that once I have this value in my hand, then I do not need to expand my 1, because 1 by z square is another term that we need to expand. So 1 by z square I can write in this way. This is interesting, d dz of 1 by z. If I do, then I will have 1 by z square with a negative sign. So that means it will be minus of this. So, minus of this quantity is nothing but 1 by z square, but 1 by z I already have the expansion in my hand. If I elaborate that, so it will be minus d dz, the expansion is this, and I need to just make a derivative with respect to z. If I do, negative sign, summation over k 0 to infinity minus 1 k will remain, and this quantity will be k z minus 1 k minus 1. So, I again have a series. You can also absorb this minus 1, you can put this minus 1 inside, and if we do, then you will have minus 1 whole to the power k plus 1 multiplied by k z minus 1 whole to the power k minus 1, k 0 to infinity. So, once you have this, you can have the expansion of 1 by z, 1 by z square expansion is in your hand, and if you remember, your function was something like 1 divided by z minus 1 minus 1 by z plus 1 by z square, something like this. So, 1 by z I have a expansion, 1 by z square I have expansion, and 1 divided by 1 by z I do not need to do anything with that. So, it will stay idle. So, I have the expansion of the entire part. So, this is the expansion Taylor this Laurent series expansion of a given function if the limit is given to us or the region is given to us. Okay, right now I should stop here regarding the Laurent series. So, we will like to do something new, which is called the residue, which is much important. So, let us directly go to that part. So, what is residue and all these things? So, let me explain you first. So, next important topic is residue. I have already mentioned this term, this terminology, what is the meaning of residue. So, if this is the function and this function, if I expand this function, in Laurent series, it will be my form. Several times I have written this form. So, now by that time you have already familiar with these things. So, minus infinity to infinity. So, if I write these things, if I write this thing, then it will be plus dot 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 plus a minus k z minus z0 to the power of k plus a minus k plus 1 divided by z minus z0 k minus 1 and so on. So, on one term I will have a minus 1 z minus z0 plus a 0 plus then a1 z minus z0 and so on. This is the entire expression that we have if I expand these things, but you should only careful about these things, this term. So, residue is nothing but a minus k. So, what is the definition of residue? Residue is the, so let me erase this. So, residue is nothing but the coefficient of the term 1 divided by z minus z0. So, if you note that the coefficient of 1 divided by z minus z0 is a minus 1 according to our notation. So, here it is equivalent to a minus 1. This is called, this coefficient is termed as residue. This coefficient is termed as residue. Okay. So, now I know what is the residue, I defined what is the residue. It is nothing but the coefficient, it is nothing but the coefficient of 1 divided by z minus z0. This is just, if I expand a series in terms of Laurent series, then there will be analytic part, there will be principal part. So, the last principal term, the last term of the principal part which contain 1 divided by z minus z0 is the residue, the corresponding coefficient is the residue. So, now we have a Taylor's, now we have a Laurent series in this form. So, I have a Laurent series in this form, only one term, as my principal part, that we normally then 1 z minus z0 plus a2 z minus z0 and so on. So, now the next question is how to calculate, the next question is how to calculate this a1 term. So, I have an expansion, this is my expansion, a0 term is sitting here. So, if a0 term is sitting here, that means I have the function, that means the function has some singularity as z equal to 0 and this is a simple pole. So, if the function fz has a simple pole at z is equal to z0, then I can expand this function in this form, because I know that the only one term should be there, because this is a simple pole of order 1, that is why the pole is 1 here, pole of order 1, that means it is a simple pole. I can expand this function in this way. Once I expand this function in this way, then it is easier for me to calculate a minus 1. How to calculate a minus 1? I will just multiply the quantity z minus z0 to the entire function. If I do the left hand side, the right hand side will be readily a minus 1 plus a0 z minus z0 plus a1 z minus z0 square and so on. So, I can extract a0, but apart from that I have also this term in my hand. So, in order to vanish this term, what we need to do? We need to just take a limit z tends to z0, z minus z0 function of z. If I take this limit z tends to z0, z minus z0 fz, if I take this limit, readily in the right hand side I will have a minus 1 term in my hand, because the other term, since there is no problem putting the limit at z equal to z0, it is an analytic part. So, at z equal to z0 this part is not blowing up. So, I can put this limit, and once I put this limit I will have this in my hand. So, this is the formula of finding the residue if the function has simple pole. So, let me write down here. So, how the residue is defined? So, the residue is normally defined as residue of the given function fz at the singularity z0 is limit z tends to z0, z minus z0 function of z, that is all. This is the recipe to find out the residue once I have my functional form and know that this is the first order, this is the singularity of first order. With this note, I would like to conclude the class here. In the next class, I would like to mention more about the residue if the function do not have the first order singularity or singularity simple pole. If you have more than simple pole, is the n order pole, how to tackle with that, how to calculate the residue, that we will discuss in the next class. So, with that note, I would like to conclude here. Thanks for your attention and see you in the next class.